Welcome back, everybody. Our first chapter this semester is going to be Chapter 16, where we're looking at NMR spectroscopy. And so we have some experience from last semester with different types of spectroscopy. Typically when you're doing spectroscopy, you're looking to determine the identity and the purity of a sample. And if you remember, we did IR spectroscopy, which was infrared. And what we did was we used this to identify the presence or absence of functional groups. And so both the presence and the absence are equally important because you want to confirm that you have a functional group present or that it's not present. So in doing IR, we would look for OH groups or carbonyls. The OH could indicate an alcohol. It could indicate a carboxylic acid. Or water. Your carbonyls could be a range of things, an aldehyde, or a ketone, or an ester, an amide. So if we just refresh from IR, we're looking for alcohols, carbonyls. We can determine if we have an alkane, an alkene, an alkyne, and an amine. Right, so these are some of the key functional groups that we looked for in IR spectroscopy. But if you recall, from IR, there was no information about the connectivity. We did not know how the carbons were connected. So for example, if you have two clear liquids, one is methanol, the other is ethanol. The molecular formula, the structural formula for methanol is CH3OH, and for ethanol, it's CH3CH2OH. Now, if we were to look at an IR, spectrum for either methanol or ethanol, you would see an OH stretch in each. Now the fingerprint region would be different. But how could you tell one was methanol and one was ethanol? The only way based upon IR would be to compare to reference spectra. Which you are familiar with this. Now what I'm going to do is I'm going to teach you how to use proton NMR to determine the structure of a molecule. And this would allow you to determine the difference between methanol and ethanol. So we've already had some encounters with NMR spectroscopy. In the fall semester we looked at carbon-13 NMR. In the spring semester we will still look at carbon, but we're going to focus on proton. Alright, so now what we're going to do, we're going to go through some theory, some basics in the theory, and then we will look at actual spectra. So let's just start with dissecting what NMR stands for. So it stands for nuclear magnetic resonance. Okay, so if we take the first part, the nuclear part, what NMR does is that it sees, and I put this in quotes, the nucleus of atoms that have spin. So when I'm talking about this, so there are NMR observable signals, NMR observable nuclei, and NMR silent nuclei. An NMR observable nucleus has an odd number of protons and neutrons. Therefore, it has spin. So some common NMR observable nuclei are your hydrogens, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. Some of your NMR silent nuclei would be carbon-12, the most abundant isotope of carbon, and the most abundant isotope of oxygen. And so these silent nuclei do not have spin. Okay. Now, if we have a nucleus that has a charge, a spinning charge will generate a magnetic field. So, at room temperature, the direction, so this is at room temperature, the directions of the fields are random. If we were to take these random randomly oriented nuclei, and then apply a field, a magnetic field. Okay, so this is apply a magnetic field. That's what B0 stands for. What we would do is that some of the spins would align. Let's go back. So this is the direction of the applied field. Some of the spins would align, and some would not. They would oppose. The aligned state would be called alpha, and the opposed state would be called beta. Now alpha is going to be lower in energy than beta. So there's some energy difference here. This energy difference is quantized. So now what happens is let's do our steps of doing NMR spectroscopy. We have our sample with randomly aligned spins. We apply B0. This will cause some spin states to be in the alpha position and some to be in the beta position. Now what we can do is we can apply radio frequency, and this is going to be a range of radio frequencies, and that will promote, when we hit it with the right energy, oops, these should be misaligned, these should be opposed. Okay, so we apply a radio frequency, and when one of those radio frequencies is in resonance with that energy gap between the alpha and the beta states, all the alpha states become betas. Now, here's your betas. Over time, you'll have decay back to the alpha state because it's lower in energy. And if you were to graph this, it would look something like this. This is called the FID, or the free induction decay. We can then use a mathematical operation called a Fourier transform, or FT, to convert the signal, the FID, into an NMR spectrum. Okay, so that is how we acquire an NMR spectrum. So if you recall, so we have the nuclear component, right? That's where we're looking at nuclei that have spin. We apply the magnetic field. Okay, that's where we get the M component, and it will flip. Sorry, it will allow for alpha and beta, and then we apply the RF to get resonance. So there's our NMR. Now if we look at the difference in energy between alpha and beta, which is delta E is proportional to the strength of the applied magnetic field. So if this was a 90 megahertz instrument versus a 300 megahertz instrument, you would see that there's a smaller energy gap for the 90 megahertz compared to the 300 megahertz. What this means is that you can get better separation of the signals with a stronger magnet. So if we were to just summarize everything that we just discussed and look at what happens in the actual NMR instrument, you would see, so here's your solution. So you have a liquid sample. So if you started out with a solid, you dissolved it in some solvent. Here you have your magnets. They're going to generate a magnetic field. When you generate the magnetic field, you get the alpha and the beta states. Then you have, here you have your RF pulse that you add, the radio frequency. This is going to switch or flip the alphas to the betas. And then you have a detector. And this is where you get the FID. And then the computer will do a Fourier transform, and the recorder records the spectrum. So this summarizes the NMR theory. In the next video, we're going to look at the information that we can gain from an NMR spectrum.